Hello, everyone. This is the first in a series of lectures covering chapter 35 of your textbook. This chapter may be chapter 34, depending on which version you have. So, for this chapter and the rest that follows, we'll be talking about another kind of wave. We've discussed mechanical waves for a while now, and now we'll talk about light. So, light is actually sometimes an electromagnetic wave, and sometimes it behaves like a particle. And both these things are true. For the next few chapters, though, we'll only really be talking about the properties of light that relate to its wave like nature. So, we'll be looking at a wave model for light to discuss topics such as reflection, refraction, dispersion, refraction, polarization, and then we'll move on to the modern physics side of things, where we'll talk more about the particle nature of light and the quantum nature of particles and so on. But for now, we'll only be really talking about the sort of understanding of light as a wave, which is what can be seen with the naked eye most of the time, such as this nice picture here of a dewdrop on a leaf, where the dewdrop here is actually reflecting off the forest surrounding it. So most of the time, right, drops of water on walls or like on a car are fairly clear, but sometimes they can act as reflective surfaces if the light just hits it at the right angle. So a bit of a history lesson for the first section is that before the 19th century, we're looking at like 1700s and 1800s. At this point, we didn't have Rutherford finding the proton or J.J. Thomson finding the atom. So there was an understanding that there were particles, that things were made of matter, but there wasn't like a full particle model to describe the fundamental building blocks of the world. And then, as far as light was concerned, you could go about it two ways. You could say that, okay, well, everything around us is made of matter, so I guess light must follow the same rules. So the general idea was that, at least before the 19th century, was that light was some stream of particles that was being emitted off objects. Anything that you could see because this stream of light particles was emitting from it. Or the other way around, that your eyes, it was believed that sometimes your eyes were actually emitting these light particles, and that's what allowed you to see objects around you. So kind of like Cyclops from X-Men, just shooting light beams normally. In around the 17th century, Isaac Newton was one of the first to design a particle model of light with explanations for reflection and refraction. And his stipulations were that particles are emitted from a light source and they stimulate some sense of sight when entering the eye, which seemed logical enough. And interestingly enough, his explanation for why refraction happens under this model, for why light bends when it moves to, from air to water, why does it bend towards the water? He said that, well, since light is particles, they have some mass, so they're gravitationally attracted to the water. So when they're at the surface between air and water, their attraction to water makes them shift closer to it. So that's why there's a bit of like an angle difference when light passes from air to water, and that's why refraction happens. Obviously, that's not why refraction happens, but it's interesting to see how, with the knowledge that scientists had of physics at the time, he was able to come up with somewhat plausible theory for refraction based on what they already knew. Now, for a while, this was the accepted model. Then later in Newton's lifetime, another model was proposed, and this one was championing light having some sort of wave-like nature, having some sort of wave-like motion. So if you think about it, right, from the understanding of the universe, things were made of matter, yes, but also things could just be propagations. They had an understanding of, mechanical waves, waves in the sea, that this energy pulses could travel through a medium without necessarily being a bunch of particles themselves, but rather using the medium to send energy. So in 1678, Christian Huygens was the first person to show and propose a wave model of light that, by considering light as waves, that could also explain reflection and refraction. And this falls in line with why actually reflection and refraction occur. It's not because, like Newton said, light particles have mass and they're attracted to surfaces in such a way that they refract. None of that. But it kind of makes a point how, right, with further testing, once you have the theories laid out, further testing and experimentations, kind of proved one to be more accurate than the other. Although we'll see that the full picture took a while to become clear. But anyhow, so Christian Huygens, 1678, proposed a wave model for light. And this wave model will actually be vindicated in the 19th century by Thomas Young. So you may have heard of the double slit experiment, which he conducted in 1801, where he basically used sunlight and some pinholes to shoot light through neighboring narrow slits. So if you just have a box, you cut a narrow slit on it, and you put it up to the sun, you'll just see like a cone of light coming in through the slit. And if you put a screen on the other side, then you just get like an area of the screen with light on it from the slit. And when you have two slits, you can keep only one open or the other one open, and either way, you should get like one little big band of light wherever the light coming off the slit hits the screen on the other side. But if you open up both slits at the same time, so now you have two small slits making two sources of light projecting onto a screen. What you see on the screen will be determined by whether or not it was true that light was a particle or if light was a wave. If light was a particle, as you can see in the bottom graph, you would expect it then to see like a fairly even band of light, whether it's brighter in the center when the cones of light from the slits maximize, when they overlap, and then it kind of fades off towards the left and the right sides as less of the particles can reach those areas. But wave theory will tell you that since you have two different sources of light, you have two different wavefronts, one from each slit. There's points on the screen where the path difference between the wavefronts reaching it makes constructive interference, and there's points of destructive interference. So along the wall, there's points where the lights from both slits will overlap and create a brighter light, those are the bright fringes. But then there's also points where they destruct each other and they'll create dark fringes. And that's actually what was seen when he conducted the experiment, leading to the conclusion that light is wave-like in nature. So this idea then of like seeing the interference of light. It's the same sort of interference, right, that we get when we had two speakers side by side, right? Depending on where you stand next to two speakers emitting sound, you will hear louder or smaller noise. So this wave behavior that we've already applied to longitudinal waves and transverse waves, things in strings or waves coming from instruments oscillating in the air, this wave behaviors were applied to light, and based on Young's experiment at least, then it was being noticed that light was acting like a wave of sound. It was acting like a wave on a string. It had these properties of constructive and destructive interference. And that said, though, light was actually not just a mechanical wave. You had the great James Clerk Maxwell, a Scottish scientist who, in the 19th century, created his model of electromagnetism, and in 1873 asserted that light was a form of a high frequency electromagnetic wave. So a lot of the derivations from relations that you study in your electricity and magnetism course have been architectured by Maxwell himself. The whole relationship between a magnetic field and electric field tied into a electromagnetic field carried by a photon is in part due to his great work. Now, he had models, he had theories, and his model of the light being an electromagnetic wave of a particular high frequency was vindicated by the German scientist Heinrich Hertz, which this may sound familiar since he had the honor of becoming a unit of measurement for the frequency of waves. And what Hertz did was he was able to use two conducting spheres to generate radio waves, and in doing so, he was able to detect them and confirm that Maxwell's theory that light was part of electromagnetic radiation. It was part of this. It was a form of an electromagnetic wave. So this gave a lot of favor to the idea that light has a nature of being a wave. And so by this point in the late 19th century, scientists accepted the wave nature of light. That said, though, there were some things that the wave model of light could not explain. Hertz also experimented with something called the photoelectric effect. He noticed that he could eject electrons out of a metal plate if he shone an ultraviolet light onto the plate. But if he had used a regular lamp, it did not eject any electrons. And he thought, well, light's a wave. Why can't we just make the light brighter, more intense to give the electrons more energy? And he tried that, and it didn't work. But when he put on a light bulb of a higher frequency light, that worked. So that's not something that the wave model could explain, and it wouldn't be until the early 20th century where you had people like Heisenberg, like Planck, like Einstein, who could come in and show that in certain cases, like the photoelectric effect, light is acting as a particle. The truth is that light has a particle-wave duality. Some situations it'll act like a wave, and in others it'll act like a particle. But for the remainder of the chapter, we'll just be discussing light as a wave. I hope you join me for that. I'll see you next time.